Okay, students, very happy to meet you again. This is very theorem in the graph theory called Wor's theorem. Okay, so Wor's theorem we are going to discuss now. O-R-E, Wor's theorem. Now, before going to the theorem there, I will explain you some concept behind that. Okay. Now, take for example. This is what a graph. Okay, and this is what we say uh, this is u, you say this is vertex is v, this is w, this is x, you suppose. Okay, now what we understand here, now what's the degree of v? Okay, the degree of v is equal to 2. Now what is the degree of w? Okay, degree of w, you concentrate on this. W and V are not adjacent to one another. It's not adjacent to one another. Okay. Now what I am doing, I am adding these two. Okay. That is degree of V plus degree of W is greater than or equal to n, where n is the total number of vertex in any graph. Okay, so in Hamiltonian graph, this is always true. This is always true. That is what we are going to prove now. For any graph, we can see this true. In any graph, you can see this. This is true. Okay, so that's what we are going to see now. Okay, so let us see that particular theorem now. Let me take that expansion for you, and we can bring here the theorem. The theorem says like this. One more expansion we can do. Okay, now it's good for us. Correct. It's very good to see to us. Okay, now what the theorem says now. Okay, now look at the theorem here. This is called the Ore theorem. Okay, what the Ore theorem says, let G be a simple graph, and the condition is that the number of vertices must be greater than or equal to 3, otherwise it's not true. That's what we have to understand. Little above we can take so that they can see the time. Okay, so next is what if u and v are any non-adjacent vertices, okay, as we see just before, then the degree of u plus degree of v is always greater than or equal to n, implies G is Hamiltonian. That's what we have to prove here. Okay, that is, if u and v are any non-adjacent in any graph, simple graph G, then and if d of u plus degree of v is greater than or equal to n, and n is greater than or equal to 3, then that G must be a Hamiltonian. We know what is Hamiltonian. I mean, a Hamiltonian path is a path which passes through all the vertices only once, and the end and final vertices are equal. Now, first, I am assuming that d of u plus d of v is greater than or equal to n. Okay, that assumption should be there, and n is greater than or equal to 3. That also we have to assume. Now what we have to prove is that G is Hamiltonian. That's what we have to prove here. G is Hamiltonian. That's what we have to prove. Now let us assume that G is not a Hamiltonian. Okay, if G is not a Hamiltonian, then what we have to get is that we have to get the contradiction for this assumption. Okay, so keep in mind that. Now I assuming that G star is maximal. What is the meaning of maximal? If any graph is greater than this, then it is a Hamiltonian. That's the meaning that G star is maximal, or in the book it is given as supergraph. G star is a supergraph. That's what given there. Okay, suppose u and v belongs to G. Since G is not Hamiltonian, by our assumption, it is incomplete. Okay, which one is incomplete? G is incomplete. Now G star I am taking as, with the G I am adding the edge UV. I am getting a new graph. Am I correct? Since this is a maxima, this must be a Hamiltonian. It's a Hamiltonian because G plus UV, it validate the G star as a maximum. Okay, so G star is equal to G plus UV is a supergraph, I am assuming, and G star must be Hamiltonian because by our G star is maximal assumption. Now note that if you see this particular statement or mathematical expression, only addition of UV will make it Hamiltonian. G is not a Hamiltonian, we assumed. When it will be Hamiltonian, it will be Hamiltonian when UV is added with G. Okay, that's what the note we have to understand here. Okay, that note will be useful at the conclusion time. Now consider the cycle. U equals U1 edge U2 V1 edge V2 edge V3 dot 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 Vn, where the Vn we are taking as V, that equals U, which is Hamiltonian as by our definition. Okay, by our definition this is Hamiltonian. Okay, right. Now let us go to the next page. This is what we have on the next page here. We have that. Okay, in the next page what we have is that, right, you can bring it down. Very good. Now that expression can be given like this. Am I correct? V1 equals U, that is initial vertex, and this is V is a final vertex. So all these vertexes are connected by the edges. Okay, connected by these edges, and U and V also connected. We also connected in G star supergraph. Okay, now I am defining a two set like this, x and y. X and y I am connecting, x and y I am constructing like this. Vi in G, the vertices I in G, if U is connected to V I plus 1. Suppose here 1 is there, then U must be connected to V 1 plus 1, 2. Is an edge in G. Okay, if this satisfies, I am putting inside this particular set. If this satisfies, I am putting inside this particular set Y. Now note that U and V does not belongs to X. See here, by the definition of the X, U and V does not belongs to X, as well as U comma V does not belongs to Y. Because U is here, V is here. It is impossible to in the individual containing this into the individual set. This is impossible. Am I correct? Therefore, UV does not belongs to X, UV does not belongs to Y implies U comma V does not belongs to X union Y. This is a conclusion for us. Am I correct? Also, you look at that the union of X. Right. I'll take the point so that you will understand that. Also, you look at that this X union Y, the X union Y is always less than or equal to n minus 2, because we have taken n is the total vertex of the graph. The two vertex are not coming into the graph, therefore n minus 2. So the total vertex in X union Y must be less than or equal to n minus 2. Also note that the length of X, the length of the vertex X is equal to degree of U, and the length of Y is the degree of V. Now, using the inclusion principle from set theory, we know that the modulus of X union Y equals modulus of X plus modulus of Y minus X intersection Y. This is not bracket, this is modulus. Okay, that's what you have to understand. Now rearrange this, you will get this particular step. Modulus of x intersection y equals modulus of x plus modulus of y minus x minus y. But this statement is greater than or equal to n minus n minus 2. So by the our assumption, the beginning, we have assumed that the sum is greater than or equal to n, and this sum is already we have seen here n minus 2, therefore n minus n minus 2 by the hypothesis. So definitely this side you put whatever may be n here, definitely will be greater than or equal to 1. So this is greater than or equal to 1, that is absolute value of x intersection y is greater than or equal to 1, implies there should be at least one vertex. See here, one vertex that must belongs to x intersection y, which implies vi must belongs to x as well as vi must belongs to y also. Okay, right. By our definition here, if vi belongs to x, then we will have here, and vi belongs to y implies we will have here. So is an edge in G. So this definitely this is an edge in G. Okay, right. Now what will take place? Now I take this next page now, and you will see that the conclusion of this particular theorem, and that will give you something very concrete idea about how these theorems can be proved. So now look at this particular picture. U is equal to v1, v2, v3 dot 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 vi, then vi plus 1, vi plus 2 dot 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 vn and v. Okay, right. This is edge in G, this is also edge in G, and this is U is connected to this in the G star. G star equals G plus U. That edges we have. Am I correct? Okay, now look at this. I am starting here. Okay, then I am going here, then coming here, then I am going here, going here, then I am coming here, then I am coming here. What I get? A Hamiltonian path I am getting. Okay, the graph is a Hamiltonian because starting vertex moving like this. Okay, then it is going like this, then it is coming again to this particular graph, and then coming here and going to that particular vertex. So it is a Hamiltonian. Am I correct? So in this Hamiltonian, there is a contradiction here. What is the contradiction? Is that U is a Hamiltonian path, but what is the condition that with the G U V you have to take, then only it will be a Hamiltonian. But without adding this UV, without adding this particular UV, okay, I am starting here, coming over here, and then I am moving here, then coming over here. Again, I am coming to this. So I am getting a Hamiltonian path. Okay. So this is a contradiction to our assumption, because G star is a Hamiltonian, maximum Hamiltonian, we assumed, and that is added UV, but here it is not added UV, but still we have a Hamiltonian path. So this is a contradiction to our assumption that G is a Hamiltonian. Therefore our assumption that G is not a Hamiltonian is wrong. Okay, and thus we can prove our theorem, and this is a way we can prove our theorem there. Okay, so in another class we will be looking at how and the theorems we can discuss that. Okay, so with that we come to the end of this particular class. In the next class we will be discussing about another theorem. So till then, all the best, and you do this again and again so that you can understand this. Otherwise you will not understand this theorem very clearly. This is the fundamental idea that we have here.